What's up, everyone? This is LeetCode 133 clone graph. So we are given a reference of a node in a connected undirected graph, and we have to return a deep copy or clone of the graph. Each node in the graph contains a value, which is an integer, and a list of its neighbors, right? This down here, right, you can read it if you want. Don't be confused by it. This is basically just telling you how they set up the test cases, right? It's basically just telling you that, like, right, its first index, so this corresponds to the first node, right? The first node has the neighbors 2 and 4. This corresponds to the node with the value 2. It has neighbors 1 and 3. This corresponds to the node value. The third index corresponds to the node with the value 3, and that has neighbors 2 and 4. This corresponds with the fourth index. The fourth index corresponds to the node with the value 4, and that has neighbors 1 and 3. I hope I explained that right. I might have messed up. I don't remember. But basically, it's first index, right? So index 1 corresponds to node with the value 1. Index 2 corresponds to the node with the value 2. Index 3 corresponds to the node with the value 3. Index 4 corresponds to the node with value 4. And these are just the neighbors for those specific nodes, right? Your actual input is the first node, right? And again, you're actually given the node as the input, not the adjacency list or anything. So you have the value and the neighbors, okay? And so, yeah, we have the original graph, right? And we can't return the original graph, right? Like, it shows you right there, right? We need to do a deep copy. You can't return the original graph. Okay, so for example, if I just return the original input node, node with value 1 was not copied, but a reference to the original one, right? So we would have an error. So we need to do a deep copy. And additionally, look down here, right? We need to make sure the neighbors are properly set up, because 1 here has neighbors 2 and 4, but here it has neighbors 3 and 4, which is not great, right? This is messed up. This is not set up properly, okay? Also, you could do something like this where you just deep copy the entire graph, like kind of using like a function, but like, of course, like you can't actually do this, right? Like it kind of defeats the purpose of the problem. You wouldn't be allowed to do this in an interview, because they want you to do it manually, right? So this wouldn't fly. But, you know, if you have to actually do it in, like, I don't know, on the job or something, this is how you would do it. So how are we going to approach this? Okay, we're going to use a hash map, okay? Right, we have key and a value, right? Hash map. And the point of that is, like, in the key, we're going to store the original node. In the value, we're going to store a copy of the original node. Or not, yeah, we're going to do a deep copy of this node. And the point of that is, like, we need to make sure we have the same order, right? So, like, when we make a deep copy of this node here, right? Right? Like, let's say we're at this 2, right? We need to check the neighbors of 2, right? So it would be, we check 1 and 3. Okay, when we're checking 1, we're going to check, is this in the hash map? Well, it is, right? So we don't need to create a deep copy of 1, right? It already exists. We already did a deep copy, so we know that we can just connect it. That way we don't have like these weird edge cases where like you have this 1 going here and this 2 like going to a different one. Like you don't want that, right? We want to properly set up our graph, and the hash map helps with that. Okay, so let's check our constraints, right? That's always important, right? You can read through these, but the really important one is this, which is that we can have 0 nodes in the graph. So we need to handle the edge case. So we're going to say, if not node, return none. Okay, now let's create our hash map. And we're going to handle this problem recursively. So we're going to say DFS node, right? And down here, we're going to call this function on this input node. Okay, so in here is basically where the bulk of our logic is going to happen. Okay, you can use BFS also. I just think DFS is a little bit simpler to comprehend. But you know, to each their own. There's different ways to approach this problem. But we're going to use DFS, okay? And so what we're going to do is, first of all, we need to check when we get into this function, this DFS function, and we're past a node, we need to check, is that node in our hash map or not? Okay. Now, if the node's in the hash map, then just return the deep copy of it, right? So we're going to say return clone node. Okay. Now, if not, then that means it's not in the hash map. So we actually need to create a deep copy of the node we were given. We're going to say copy equal to node.val, right? And we need to insert that into the hash map, right? And we need to return. But before we return, we need to handle the neighbors of that given node we were passed as well, right? And do a deep copy of those. So what we're going to say, we're going to basically handle the neighbors recursively, cloning them, or handle the neighbors by recursively cloning them, right? So we're going to say for neighbor in node.neighbors, because remember we have a value for a node, but we also have neighbors, right? So we can just call this here. Okay, we can call this on the actual node that we're given. Okay, now for these neighbors, right, we need to basically append these neighbors in our copy, right? So we're going to say copy.neighbors.append dfs neighbor. Okay, now I think most of this code's pretty easy to understand. This might be where you get lost. So I'm going to explain this. What we're doing here is basically, when we're at this 1, right, we already made a deep copy of this 1. So we're checking the neighbors 2 and 4, right? If we don't have a copy of this 2, let's create it, right? So we create this deep copy of this 2. And so this 1 has a deep copy of the 2. This 1 has a deep copy of the 4 that we make. Now let's say we're at this 2 and we're looking at the neighbors here, right? We already have a copy set up because we already, well, this is the first node that we deep copied, right? So when we're at this 2 and we're checking the neighbors, we're not actually doing any of this. We're actually going in here and basically just returning the copy node, which is 1, for the neighbor of 2, right? So that's what this is doing. You're basically checking the neighbors. When we're at a given node, we're checking the neighbors. And for the deep copy, we're basically checking, okay, for this deep copy, let's check the neighbors. Okay, does this 2 exist as a deep copy, right? If not, let's create it. If it does, right, just return the actual deep copy of this 2, right? Or whatever node we're from. Okay, so that's basically what we're doing. So there's really 2 cases when we're appending the neighbors for the deep copy, right? Is we're basically checking, does it exist or not? If it does, then we're just returning the deep copy that does exist and appending that as a neighbor. Otherwise, we're actually just going to create it. Because again, we're doing this recursively, right? So just keep that in mind that you're doing this recursively. Yeah, should be it. And it is. Okay. So this problem isn't too hard. I think, I don't know, like you just gotta keep in mind that you're doing this recursively. So you gotta understand what you're doing when you're actually on this line. I think this is probably the line that you need to wrap your head around the most, and this problem will make sense to you. Because I feel like all this other stuff is kind of easy. But yeah, just know what's happening here, and you'll be fine. Okay. Anyways, I hope this helped, and yeah, peace out.